I guess this is still a starting point, but I really hope to see more types of gravitational waves. For example, like signal from a supernova, signal from a single rapidly spinning neutron star, and those weaker waves and different types, and which might bring us different information from the universe.
It's trying to work out how the universe works, how the cosmos works. With gravitational wave detectors, we can see a whole new type of spectrum to investigate what happens in the cosmos.
We've seen a few gravitational wave events over the last 7 years, but only one that was ever seen in electromagnetic waves, that is light. By observing them in the electromagnetic spectrum, we can learn so much more about them than just with gravity alone.
It's just amazing. Every time when we start an observing run, I'm getting all excited and try to work out what we're going to see next time. 24th of May, we will start 04, that's the 4th observing run. 18 months, yep. And that's new sensitivities, new systems being upgraded. The big source we're after is some more binary neutron star mergers. Partnering up to doing this great science is for myself a super exciting endeavour and research for me to do. I can't be on site as much as I would like to be, so hence this remote facility, what we have here at ANU, will also help me to be part of that work, what we do in the US.
I'm here in the main control room of LIGO Hanford Observatory, and ANU is setting up a smaller version that will be able to look at the same stuff so we can assist in the work.
So this room is set up so we can actually directly interface with all the computers and the controls in the LIGO gravitational wave detectors in the US. So there's 2 detectors, and from here we can actually measure and report what is happening. If there is something amiss, we can help investigate.
You can see we have a lot of the screens here which monitors the detector's behavior, its status, whether it's stable, and is there any noise disturbances, earthquake, things like that.
The detector is a very complicated instrument. You need to look in a lot of different places to verify your measurements and to sort of find out what is causing a certain type of noise. Part of the reason there's so many screens behind me is these are all monitors for various subsystems, so people can kind of cross-check while we're running.
Yeah, that's actually very important and very convenient. You know, we monitor so many pieces in the detector and anything can change in real time. This just makes my life so much easier. That's next door to my office. I can walk in here and look at multiple screens and look at the status of the detector and the output in different channels.
So Australia has by history a large involvement in the LIGO gravitational wave detectors, building it up. And we have expertise to help build and commission and operate the interferometer, and with this gives then ANU a big contribution again to running the observatories in the US.
The setup of this remote control room facility really kind of connect the group here with the sites. Jenny, our colleague, is working there at the moment. We're kind of feeling that we are working as a group, although we are separated in the 2 ends of the world. So this really makes us to feel that we are in the center of this observing run.
So what is the new in a 4th observing run is that we increased laser power. We have new coatings on our mirrors. We have a new means to control the squeezing or the quantum state of light.
We use a technique called squeezing to improve the quantum noise in the interferometer. So that's noise that arises as a result of Heisenberg's uncertainty principle. And basically, this happens because we have mirrors in the interferometer and we measure the mirror position by hitting them with photons. Pushing the mirror with photons changes its position, so this introduces an uncertainty in the position and the momentum of the mirrors. Squeezing is, at the moment, not totally optimized in the interferometer. We're not getting quite as much power out as we think we should get, and that might be harming this sort of quantum technique they use. So we're trying to understand that.
We have now about 400 kilowatts of circulating power. Previously it was like 200, and because now we're going so high up, there's a lot of heat dissipated in the mirrors we use, in the glass we have. And although it's very pure and pristine and beautiful glass, it's still, with a lot of power, it still starts absorbing, and that shapes the mirror wrongly, in the wrong way. So we need to compensate that, and there's a lot of effort to counteract that one, and that is actually our biggest challenge at the moment. One of the improvements for the fourth observing run is installed a filter cavity which controls the quantum state of light.
A lot of the signals we see, they will start at a low frequency and then they will sweep up in frequency. So we want to increase our broadband sensitivities.
And for the low frequency, that will improve the signal to noise for the ring down signal, and at the higher frequency for the merger signal. And it is across the band an improvement.
Before LIGO installed it, this technique had never been used on this large scale anywhere in the world. So it's really, really exciting, and it makes the detectors kind of quantum instruments now.
It has been 3 years we haven't been observing. So, right, the last one ends early 2020 and was when the pandemic started. Now it's almost 3 years. Our detectors are much in a better state, and the sensitivity is the best so far. So we would expect to reach much deeper into the universe. And obviously we will see many of these merging systems of compact binaries, black holes and neutron stars.
I'm always flabbergasted when I think about binary neutron star mergers. Those binary neutron stars, or those neutron stars, they are the mass of the sun, but in the same area as the size of Canberra. And if you just think about that, it's just insane. And then you have two of those, and then they merge and they will make this massive explosion in the universe somewhere. And that's what we then see with the LIGO detectors.
We've seen one event where neutron stars hit another neutron star, and that resulted in an electromagnetic signal that was observed over a broad range of wavelengths from the radio all the way to the gamma rays.
We are very excited to observe the astrophysical signals, the merging binary neutron stars, with not just the gravitational waves, but the electromagnetic counterparts.
We've established a new facility. The facility is robotic, so there's no human intervention at all. And the idea is to be on these targets as soon as they're discovered. The robotic telescope means that we're going to be on the target probably a few minutes to an hour after the optical counterpart is discovered. And that's much faster than you can do with humans in the chain. We've never seen an electromagnetic signal from the merger of a neutron star with a black hole. There are some theories there which predict that there should be an electromagnetic signal, but we've never seen one. The first one, yes, I happened to be on the telescope at that time. I heard rumours of something big that occurred, and once it was officially announced through astronomical telegrams, and we stopped what we were doing, and we then went and observed the target. This was about a couple of days after the event. It was something that was evolving very quickly. So by the time we observed it, it had already been a couple of days, and you could see that it had cooled down a lot. So the spectrum was quite red, so quite cool, which really highlighted the point that if you really want to learn about these events, you've got to be on it very quickly. And that was the impetus for automating the telescope, because these events evolve very, very quickly on the timescale of hours. The ANU 2.3 metre telescope is based at Siding Spring Observatory. It has a very powerful spectrograph called WIFES. So it's a combination of a relatively large diameter telescope with a very efficient spectrograph and automatic operations, which makes this a really unique facility.
One of the great outcomes of detecting and investigating the boson interstellar merger is finding out where the heavier metals come from in the universe. You know, we work out where golds come from.
We will have many more detection events that will help us to better understand the whole population.
I think there's been about 100 events. We see black holes merging which are larger than what one would normally predict from stellar evolution. So supposedly these have already merged, unless our stellar evolution models are wrong and we are able to produce black holes of this mass. So that was a surprise.
It's important to observe both gravitational waves and electromagnetic waves for these gravitational wave events. That gives us an alternative way to measure the Hubble constant, which tells us how the universe expands and for us to better understand cosmology.
Because there's an argument between 2 or 3 or 4 different values, and each different way of measuring it seems to give a different answer. So if we could sort of weigh in on this argument, we could like narrow down which Hubble constant is the correct Hubble constant.
There are several predictions from Einstein's theory of general relativity which can be tested. And one of the ones which I am absolutely amazed of is the idea that once you have one of these events, you've permanently distorted space-time. It's a very small amount. I don't know if we can test it. Apparently this is what Einstein's theory predicts. And also measuring the spin of black holes as well. That'd be a very interesting thing to do.
What might be more exciting is we see something unexpected. That's always the best.